errors. Okay. So the first thing that'll be different between a t-test and a z-test is you do a t-test for conclusions about mu, or about p. Wait. I feel like I got all discombobulated just now. We do z-tests to make conclusions about p. T-tests are to make conclusions about mu. So as we write our hypotheses are not going to be p equals. They're going to be mu equals. Do you guys need me to use the microphone? I figure if you guys don't, they should be fine, right? Yeah. Can you guys even hear the jackhammering that's going on over there? It's super distracting. It's been distracting all day. Okay. So guys, let's go ahead and look at this particular example. What should I use for my null hypothesis in this case? That the true mean is equal to 30. And my alternative? They were hoping to make the battery life better, so they would want to use a greater than 30. And do you guys see now why this hypothesis, which a lot of you wrote, made me upset? Instead of, like, you need to use which parameter you're talking about. We use mu for means and p for proportions. Okay? All right. And so you guys, if we're doing tests, we now have the ability to make type 1 and type 2 errors. So which one was a type 1 error?
Reject the null hypothesis even though it's true.
The null is true and we reject it. Okay. So in this case, what would a type 1 error be in this case, like in context?
Maybe it is 30 hours, but we conclude that it is greater than 30.
Okay, so the true mean battery life is 30 hours, but we conclude it has improved. And you guys, as the company is trying to improve their formula, I can't help it.
I know. It's just like
What? So what's the consequence of that error?
we assumed that the change was productive, but it wasn't.
I mean, that's another way of describing the error. What's the consequence of assuming they improved the formula, but they didn't?
They marketed it wrong.
False marketing, for sure. What else? If their goal was to improve the formula, and they think that they did, are they going to stop trying to improve the formula? Yeah. All right. What's a type 2 error in this setting then?
It does improve, but it concludes that it doesn't improve. The battery life improves.
Yeah, the mean battery life has improved. Oh, that should be true mean battery life. Has improved. But we fail to reach that conclusion. And what's the consequence of that? What's the company going to do? They're just going to keep trying to improve, yeah? All right. Now, in this setting, is one of these errors more serious than the other? Which one?
Type 1.
Yeah, type 1 would be a pretty big deal here. And how often do we make type 1 errors? Whatever alpha is, yeah? If we use alpha equals 5%, we're going to make a type 1 error 5% of the time. Everybody good? Cool. And we said a type 1 error is more serious, yeah? So doesn't that mean maybe we want a lower alpha? Because if alpha is the probability of a type 1 and type 1 is more serious, let's use the lower value for alpha, right? Do you guys get what I'm saying here? Okay, so all right, so we're gonna keep going with this example where we take a sample of 15 batteries and we want to run this t-test. So let's go ahead and check our conditions for the t-test. But I've got great news for you guys. The conditions for a t-test are the same as the conditions for a t-interval. Nothing's changed at all. So how do I check my random assumption? What was given? Given SRS. Okay. What about normal? N equals 15. Do we have to draw a graph? No. Did I give you some graphs to look at? Yeah. I gave you dot plots. I gave you a box plot. I gave you something called a normal probability plot. Which one do you want to use to check this condition? The dot plot. You could also use this one on the left. This is called, like I said, a normal probability plot. And the closest, essentially what this is for this point, it takes the z-score for its percentile, if it was normal. Okay, and plots it. And so the closer this graph on the left or on the right is to a perfectly straight line, the more normal that sample is. But let's go ahead and use the dot plot. Now, if I give you multiple graphs and you say the graph, then you're not being specific enough. Okay, so we're going to say the dot plot of the sample.
Could you just describe it using the letters that were given
Yeah.
to the graphs? Okay.
Is mound-shaped and approximately symmetric.
Do you have to say the shape, or can you just say like implies normalcy?
I would just mention the shape. I would use the word approximately, though. Unless it's perfectly symmetric, you should use the word approximately. Cool. One more thing. Independence?
I was gonna ask a question.
Sure.
How would you notice it was like? Can you just say approximately symmetric? Because it's not really mound shaped, or at least I can't see how it's mound shaped.
I think it's mound shape.
Okay.
I mean, the word mound shaped, remember, like, we're describing a sample. We're not trying to, it doesn't have to be anywhere close to perfect. It just needs to look like when I look at this, let's put it this way. I don't see a major difference between these 3 points and these 3 points in terms of mound shaped. What I see is like some points on the end, but the bulk of the points in the middle. And if we were to make, say, a histogram where we put each of these points in bins, it would be very much a mound-shaped histogram. So dot plots can be a little bit deceiving, but I think this one looks fine. All right. Independent? 15 is, in fact, less than 10% of all batteries. If I owned a battery company and it was only making 150 batteries, then my company's not going to be very successful, right? All right. I'm sorry?
Maybe if they're really good batteries.
They'd have to be really good. But their battery life is 30 hours, so I'm going to go with not that good. Yeah. All right. Next. Test statistic. Guys, my posters with the formulas will be back up, but they're giving me a whiteboard and I needed to mark where it's going to go. But the formulas will be back up, okay? And a reminder that a test statistic the formula was stat minus parameter over the standard error. Okay? The statistic I have here, what is it? If we're trying to make a conclusion about a mu, a population mean, what should my statistic be?
3 hours.
No. What symbol do we use for the a statistic? Is the sample, yeah? So the statistic for the population parameter mu is going to be the sample mean. What is the sample mean? What's the symbol for the sample mean? X bar. So to calculate our test statistic for these, we're going to do X bar minus our parameter that we're going to assume to be true is the mean of the null hypothesis, which will be the 30 when I calculate it all the way out. Okay? And then the standard error of these is is S over the square root of n. So this is the formula with which you can calculate your test statistic. Now, if I do that in this case, our t statistic would be 33.9 minus the 30 from that null hypothesis divided by 9.8 over the square root of 15.
$1.54.
1.54? Cool. All right. The next thing I want to talk about is finding the p-value from a test statistic. Okay? So what you're going to do is draw a normal curve. And we're allowed to draw it as normal because we said up top that the normal condition was met, which means it's safe to assume that the x bars are going to be approximately normal. Now, the one we're going to draw is the distribution of t's, not the distribution of z's, because this is in fact a t-score. Okay? The distribution of t's is centered at 0, but instead of using the standard deviation, does anybody else remember what we use? My degrees of freedom. And how many degrees of freedom do I have here? 14. Cool. And what was our test statistic? 1.54. Can I throw this into normal CDF? What's wrong with throwing this into normal CDF? Normal CDF is going to ask you for the standard deviation. So instead, let's look if there's anything else there that can help us. Option is it number 5, I think. Option number 5 in that second VARS menu. Option number 5 is TCDF. And other than that, it's the exact same idea.
TCDF?
Mm-hmm.
6.
TCDF is the one you want.
Where?
Should be at second VARS. It's number 6.
6.
So I'm just going to throw some feeling out. And then right back to it, should have everything. There's because there was stuff before.
Okay.
I use the thing.
I want to, but I have to around now. I see softball every single day.
0.07?
Please.
Yeah.
Do you put that as the upper or lower?
Your upper or your lower would be 1.54. Your upper would be a gajillion. So you remember those upper and lower are describing the boundaries of what you're shading. Okay. Now, you guys. I've helped a bunch of you with test corrections from the previous test, yes? Some of you still have work to do on those. The question by far that got everybody most stumped was number 8, in which I gave you the test statistic of z and asked you to calculate a p-value. It is reasonable to assume that I'm going to check to see if you learned from your previous test on if I give you just the critical value, can you find the p-value? Do you guys get what I'm saying here? So, do we all understand that the whole premise of the way your calculator, when you do a shortcut in your calculator, the way it calculates the p-value is it does what we just did. It's just programmed to go straight to the TCDF. Does everybody understand what I'm saying? Okay? So, if I give you a t-score, do you now know how to find a p-value? How do you do it? TCDF. Now, if I give you a z-score, and I ask you to find a p-value, can you do it? I can't hear you. You can just use normal CDF to do it. Is everybody good?
Say that again.
If I give you a z-score for my sample, normal CDF can get you the p-value. If I give you a t-score, TCDF gets you the p-value. There's one last thing I want to bring up. How did I know to shade to the right here? My alternative hypothesis was strictly greater than. The next example, we'll do a not equal to kind of go over that one more time. Okay. All right, now, that p-value being 0.07. Can somebody interpret that p-value? Which, by the way, is one of the more challenging things to interpret. Because I'm not asking you to tell me what conclusion we should make. I'm asking you, what does that 0.07 really mean? Well, are you guys with me that p-value came directly from my t statistic? And my t statistic assumed mu is equal to 30. Okay, so our p-value is calculated as assuming the null hypothesis is true. So, if I want to interpret the p-value in context, I might say if the true mean battery life is 30 hours. Then the probability we could get a sample mean of, and what sample mean did we get? So, we have to decide now, does us getting that 33.9, does that tell us, does that make us comfortable saying the mean battery life has definitely improved? Or is it reasonably likely that you could get that 33.9 by chance?
It's probably improved.
How do we make that call?
Well, it depends on what alpha is.
It depends on what alpha is. Okay, hold on. And we just said alpha was the probability of a type 1 error. Everybody with me? So let's go back to that real quick. Go ahead and say, what conclusion can you make at alpha equals 0.01? This might be one of those cases where we use a really low value for alpha because the p-value or because the type 1 error is so much more serious. All right, so now how does 0.07 compare to 0.01? It's greater than 0.01. So what does that mean? Are we rejecting or failing to reject? So, grand scheme of things, is this that different from the other tests that we already know how to do? And it's pretty much the same idea, okay? All right, so let's look at another one real quick. I'm gonna let you guys read this at the top. All right, now we're at the place where I'm going to start throwing in every once in a while some quick questions from, say, Unit 1 to help us kind of work through, start reviewing some of those concepts that are really easy to forget. Okay, so does anybody remember the rules for deciding if something is an outlier or not?
It's like 2 standard deviations away from the mean.
It could be 2 standard deviations from the mean, or 1.5 IQRs away from Q1 and Q3. Okay. Now, the 2 standard deviations rule is really good when we know our population that we're drawing that sample from is normal. If we don't know that the population is normal, IQR is a little bit better approach. Okay, so if the initial distribution that we're dealing with is like super skewed to the right or something, we don't use the 2 standard deviations rule. Everybody okay? And in this particular case, we don't know the shape of the distribution we're trying to decide these outliers on. So we're going to use the 1.5 IQRs rule. So essentially, something is an outlier if it is more than 1.5 IQRs from Q1/Q3. Low outliers are too far below Q1. High outliers are too far above Q3. All right, so you guys, what's the IQR? How do I find that? Okay, so that in this case would be 34.115 minus 29.990. Is that right?
Yeah.
Cool. So if something's too low, I'm going to do Q1 minus 1.5 times the IQR. So in this case, that would be 29.990 minus 1.5 times 4.125. And if it's too high, it's 1.5 IQRs above Q3. So can somebody help me out with those two numbers? And 43 point, sorry, what was the,
Oh, 40.
okay, you guys, do we have any data values? Even though we don't have the raw data, do we have enough information to decide if we have anything that's outside of this range of numbers? We know the minimum is 26.4, so we don't have anything lower than 23.8, right? And the maximum is 35.5. So because the min and the max are outside of these ranges, or inside those two numbers, okay, no outliers. And I figured this might be the kind of question would start to drift away from what we remember. All right. So now, the whole idea is this is about a farmer who put irrigation in his fields and he wants to decide. He gathered this sample in order to determine whether or not that new irrigation system, or if from one year for the next there was a difference in weights of these pineapples. Okay, so if that's the case, we should do a test to decide has it changed in any sort of significant measure. So, looking at this shell, what do you think my null hypothesis should be?
W equals 31.
Mu equals 31.
Why would you just have it be a variable? Or are we treating mu as a variable?
The whole idea is we want to communicate that we're looking at a mean. So we want to use the symbol for the population mean. Though they would let it slide if when we define the variable, you said W equals true mean weight. But if you just say W equals weight of pineapples, you're not communicating anything about it being a mean. And that's an important idea to them. What should my alternative hypothesis be? Why is it not equal to? Because the question specifically says, has changed. It doesn't say, did it get better, or get higher, or get lower. It just said, is it different? Cool. And what do you think we should do next? You have one of two things I think make sense next. Define the variable. Mu equals the true mean weight of pineapples for this year. And after that, before we do the conditions,
What test?
this is a 1 sample t-test for mu.
Will they like document points for where you put the one sample t-test?
Now they typically will do, did they include, they like think of it as a checklist. And in this first box, you have to have the 3 conditions checked correctly, the procedure named, and the hypotheses. And if you have all of, and the defined. So if you have all of those, you get an E. If you have 4 of the 6, you get a P. If you get less than 4, you get an I, something like that. Is usually how the rubrics read. Hey guys, can you help me with this random condition? It was given that we have a random sample? Normal. N equals 50, which is greater than or equal to 30. It's always happy when we have a large sample for means. Independent?
It's a large field.
Yeah, 50 would be less than 10% of pineapples in a large field. Cool. All right. From here, we're going to go ahead and calculate our t statistic. So my statistic is going to be x bar, so that's 31.935 minus my null hypothesis, right? My parameter is what we're assuming to be true of the from the null hypothesis, so that'll be 31 all over. S is the standard deviation, so that's 2.394, excuse me, over the square root of our sample size, which is 50. Okay, now to find our p-value for this one, we'll draw the curve. What's my degrees of freedom here? 49. Okay, we have 2.76, which is going to be this one. Now, since this is a not equal to, do we shade just one side or do we shade both sides? Both sides, so I'm going to do the 0.928 or the 0.276 on the left, and I'm going to do negative 2.76 on the right. And it's possible for those of you still trying to think through how do you do your test corrections for number 8, you should have a picture that looks very similar to this. And then how do we find the p-value from here now that we have our picture? TCDF. What are we getting?
A very small number.
That's okay. It's supposed to be pretty small on this one.
0.0081.
And that was the combination of the two?
Yes.
So, like, for instance, you got this one was 0.004, and then this one would be
I found
0.0.
the middle, and then I did 1 minus.
Yeah. So, but that's so any one of those tails is 0.004, the middle, or you could do 1 minus the lighter area there. Okay. Cool. And you guys, that makes my p-value 0.08. And by 0.08, I mean 0.008. That's what I said. Ellie, I saw your head jump up. Cool, wait a minute. So what conclusion can we make? I didn't give you an alpha, but for pretty much any value of alpha, this is less than the smallest value of alpha we've ever used. So I'm going to use 0.05, but it really wouldn't matter in this case. We can reject H0, and therefore we can conclude the true mean weight of pineapples has changed. All right. Now, the farmer did this because he put in a new irrigation system. Can we conclude that the irrigation system caused the change in the weight of the pineapples?
No. Because there could have been other factors. It wasn't like a test.
Well, we just ran a test. We did a one sample t-test.
It wasn't an experiment.
It wasn't an experiment? Okay. What are some other factors that could have caused the change in the weight of the pineapples? Weather, right? Amount of sunlight. How about soil quality? Like maybe the first one, they improved the soil by using like a fertilizer or something, right? So what would he have needed? What would this guy need to do in order to prove that it was the irrigation system that caused the change?
To have like one group with the old irrigation system and one with the new one.
Perfect. Okay. All right, this is a pretty decent time to take a... They did not do it to meet the random condition. That is a fringe benefit of the fact that they did it. Okay, but that's not why someone would do it. Yeah?
They would figure out, and this would be, like, they would think that they're more depressed on certain days, and so you wouldn't really know for sure.
It's not so much about what they would be thinking, though certainly that could be a part of it. Yeah?
Is it about independence?
It is not about independence.
It's about like the ability to conclude or what you conclude on.
Okay, so the first thing I want to make sure we understand something, and you're pretty much all kind of hitting at it without hitting at it the right way, okay, is when we talk about the why of any randomness, okay, it has nothing to do with being allowed to run the test or to be able to make a conclusion, okay? It's what makes our conclusion a valid conclusion, whether it be a cause-effect conclusion or a sample generalized to the population conclusion. The reason we want a random sample is not so that we can generalize to the population. The reason we want a random sample is it means our sample will be representative of the population. Because the goal of the randomization is to make the sample representative. Now, the benefit of the sample being representative is you're allowed to generalize it to the population. Do you guys see there's a subtle difference there? Okay? Now, Random assignment is a little bit different. So the goal of random assignment is to eliminate confounding variables, but when we say eliminate confounding variables, we should have an example. So here's my example. I want you guys to think about your mood on Wednesday and Thursday. And imagine we gave you the placebo on Wednesday and Thursday. And think about your mood and your depression scores. Everybody with me? And I would like you to then compare those same mood and depression scores to today and tomorrow. How was your mood on Thursday and Friday, or Monday, or Wednesday and Thursday of last week? How was everybody's mood?
Terrible. It was the end of a long week. I was tired.
Oh, really?
Wednesday
I felt like most people were riding pretty high on Thursday. Like, yes, 4-day weekend. Whereas today, it's like, you look down. Did anybody look at the school calendar for the next 6 weeks?
It's like no breaks.
There's none. It's going to be a long haul, if you know what I'm saying. You guys catch my drift here? Okay? So, are there things within a calendar that could influence mood?
Yeah.
Yeah. What if, like, on the day they took the placebo, it was a day like today, and the day they took the caffeine was a day like a really rainy, gross day? When it's really rainy and gross outside, does that affect one's depression? What if they're...
Like, I
Some people
was just
like
gonna
it.
say, like, so many different things for so many different people are what affect
Well,
moods.
I mean, the other
How
way
can
too,
you
like if you
guess?
like rainy weather and it's a rainy day, then you're gonna be more sad on a sunny day.
So either way...
I don't know if that's true, though. Like, for me personally, I don't think that's
Well, we never care about any one individual person when we're doing this. The whole point is we're trying to get this to apply to everyone.
So
Okay.
this is a generalized thing that bad weather causes bad mental health.
If it could, we need to account for it. And so we would want to make half as many in the... Can anybody think of reasons why 2 separate days or 2 different time periods could influence people's mood?
Test.
For students, it could be if you have like tests and stuff like that,
Or if it's
versus if you have an easy week versus a hard week, for sure. What else?
If there's some like widespread like global or national incident or political thing.
Can there be news stories that make everybody sad?
Like if
That influence how people are going to respond to depression? I can think of several news stories that like make me just go. You guys know what I'm saying? Okay, and when that would definitely influence my mood, which would influence this. Okay, and as long as whatever that confounding variable is would influence all the participants, or could influence all the participants, you don't want all the caffeine to be on one of those days, or all the placebo to be on one of those days. But if half the people are taking a placebo and half caffeine during the sad days, then those sad days aren't overrepresented in either treatment group, is the basic premise. Okay? So we might say something like confounding variables. Such as sad news events, weather, etc. Will be present for both caffeine and placebo. What if these 10 volunteers were students at Ohio State University and one was before the national championship game and one was after the national championship game? Would that make a difference? Probably. All right. So, So now we want to decide, did this make a difference? Okay, so we're going to go ahead and carry out a test here. There she is. The dancing walker. Do you think she's aware of how much entertainment she provides to the people in this building?
I think she knows. I mean, I do honk at her every time.
I hope to God.
In a positive way. I'm like, beep, beep.
I hope to God I'm like,
Now.
I hope to God I feel that like happy as you know what I'm saying?
Same. Like, I wish. It like makes the day.
Maybe she has like happy people.
It's my favorite thing about this classroom. By far, my favorite thing about this classroom is I sit and watch people come in and out, and when she walks by, it's hilarious.
People watching this so much. I need her playlist. Her whole Spotify account, like, so good.
All right, you guys, what kind of data did we say this was? This is paired, so we're going to do a paired t-test. So when it's paired, it's going to be for the mean difference. And before we can find the mean difference, we should probably find each of the individual differences. Now, do you guys want to do caffeine minus placebo or placebo minus caffeine? It really shouldn't matter.
Placebo minus caffeine.
I knew you guys were going to say that.
It's because the ones on the right look bigger than the ones on the left.
I know. Students don't like negative numbers, and I get why, but it doesn't make a difference, but it does, if you know what I'm saying. All right, so are you guys cool if we each go down and write out these differences, because we're going to need them? So this would be 11. If at any point you guys want to double check my arithmetic, it's not a terrible idea. All right, and from here, what do you think we should do next?
Do we put this into L1?
We can. If you guys want to put those into L1, that works. I think I already have mine in. Then what? Once we get it in? Now what? We can't really run, we shouldn't really run the test yet because we haven't set it up. So help me set this test up, you guys. What's the very first thing we need? I'm sorry? The hypothesis 1 and hypothesis 2? Oh, I see why you're thinking mu1 and mu2. No. Because we're only running, there's a difference between doing a 2-sample test, which is what we're going to start next week, and a paired test. We're still only running this on one set of numbers, so our null is going to be not mu1 minus mu2, it's going to be mu d equals 0.
So these are like not the same thing. If you
They're not.
So you can't name the procedure
And we actually, part of the notes next week, will be focusing on that specifically. Because there is a different, so there's a paired t-test, and this didn't happen in the proportions, which is why it's not, we haven't talked about it yet. There's a difference between a paired t-test and a two-sample t-test, and we'll spend some time talking about when to do which one, okay? But like the data that we want to perform this procedure on is this set right here. It's not going to be find this mean and then do it. We're going to look at each person as individuals. Okay. So, mu D is going to equal the true mean difference in depression score. And again, I'll remind you guys, we did placebo minus caffeine. I really like to make sure I communicate that. Yeah. I don't know. Should it be greater than? Or that's what I wanted to get to, the reminder of the placebo minus caffeine first. Okay, which one would we want this? Which way would we want that sign to go? Greater than or less than? Greater than, because since we did placebo minus caffeine, we would want the greater than to be, the placebo to be bigger than the caffeine, right? And had we done that the other direction, that would be a less than 0. Do you guys see what I'm saying there? That we have to think that through. Yeah.
Sorry, I was just thinking about depression score. For some reason, that's like funny to me.
Why wouldn't it be just not equal to?
Just like
Because if it's the effects of caffeine withdrawal, that could be a positive thing as well, right?
this just doesn't make any sense.
Oh, would it increase depression? Okay, I'm reading the first line. I'll explain the last one. I gotcha.
All right, cool. So, from here, y'all.
Do you have any grid paper, like 1-inch grid paper? 1 inch by 1 inch?
It depends. Who's your favorite teacher in this building?
It's Meister. Yes. Yes. Is that a 1 inch grid? Yes, dude. This is next forget. Thank you. I'm gonna just sit back here and cut it. That's not annoying, is it, Tucker?
I wouldn't have done it if she wasn't being so quiet. Those are delicious.
Do you want some queso to dip them in?
Ooh.
There's some queso in the fridge. Cluster truck Tuesdays. Teachers do cluster truck on Tuesdays, and I got chips and queso. Hey guys, is the random condition met? Yep. Remember that note I left you?
It'll add like 2.
I feel like I want to cross like one thing out.
I'm sorry. I'm sorry.
I don't understand why you didn't take it down to your room to cut it.
That would have been the same thing to do. The thing that doesn't irk Miss Meister.
I think we should issue an apology to the people below us.
What?
you just crush my measuring tape?
Oh. Fine.
I think you should leave.
It's your measuring tape.
For my bouncy ball activity.
Wait, what actually?
Thanks. Sorry.
You know the best? Is this has been recording this whole time. Get out.
Ooh. That was funny. Anybody?
Anyway. Hey guys, is the normal condition met?
Probably. Because otherwise we wouldn't do it.
That's a good way to look at it.
I mean, like, it's probably mound shaped if I had to guess. Like, otherwise they wouldn't give us the question.
So what you said was, I don't know, we should check to see if the graph is mound shaped and symmetric. That's what I heard.
Sure.
I heard
That's what I chose to hear. Yeah. So
What I chose to hear.
This is selective.
Yeah, we don't have space for
I'm
that.
sad faced by all of my things now because you do it. Are they gonna dock me points?
no, they won't dock you points. Especially when everybody from Grandview does it.
Do we need to?
No. I can count by twos, it's fine. She just has me all discombobulated. She's the worst. Notice, guys, we're doing a graph of the differences, yes? Does that make sense as to why we're doing a graph of the differences?
That makes sense. Yeah, I'll be honest, this does not look very mound shaped. But I'm gonna say it's mound shaped enough. It's like plateau shaped.
How is that mound shaped?
I think we need to have like a conversation about what makes something mound shaped versus not.
Doesn't it just mean most of the data is in the middle of the graph?
Not necessarily in the middle. The symmetric would be mound shaped and symmetric would be in the middle, but we have a general like we expect a little bit more out of mound shape than it's actually there. So just for kicks, I'm gonna do this real quick. I'm gonna draw a histogram off of this bar chart. So let's see, and I'm gonna make it the bin width 4, so it's gonna be like kind of like that. So the first one is 3 units high, the next one is gonna be up to 4 units high. This next one is gonna be 0 units high, then 2, then 2. It's close enough.
That looks like
Alright.
for the what's
That is not
behind
mound
Alright,
it.
I'm sorry, that's not mound shaped at all.
Ooh.
I mean, well, if
That
you
is
just look at the
frighteningly
top bit
fine
to the
photo.
middle, it's still
fine.
off. That is still smooth.
All right. See, you guys are making me do this. This is your fault that I'm doing this.
Uh-oh.
Sorry.
Do you have the distractions we've had during class?
Uh-oh. Oh.
So basically, if it's like, if we have to prove the normal condition, we just draw the graph and then say that it's mound shaped.
Draw the graph, put 5,000 on there and see.
Because is it always going to be mound shaped? That's my.
It's always supposed to be, yes.
So yes.
So we'll say
So-
mound
so you
shaped and
just say that
approximately
it's
symmetric.
There, that's not right. Something's not right about this. Well, it's saying I don't have any points in between 9 and 11. And it's saying I don't have any points in between 11 and 13.
It also says that it goes up to 20. It goes up to 19.
Well, that's because I set it to that. Oh, that's why. I tried to graph both lists at once.
There we go. See that?
What I'm saying is it's very manipulatable. So what if I made my bins 5? Or what if I made my bins...
This is all skewed.
What if I made my bins... Or what if I started at -3? Like, it's all manipulatable, is what I'm trying to tell you.
Then if it's
take
all
your word for it.
manipulable, then how is it being mound shaped anything to do with normal?
So, I'm going to say this, we kind of talked about this last week, but it doesn't have to, the sample does not need to be normal. The sample needs to suggest it's coming from a population that the samples, are you listening? Because I'm trying to explain what, are you sure?
Yeah, sorry. He was
I'm trying to answer your question though.
Yeah.
So, okay. The sample does not need to be normal for the X bars to be normal. The sample just needs to come from a population that is shaped in such a way that the X bars will be normal. So it doesn't have to be anywhere close to perfect. It just needs to be close enough. So if I had a population of this shape, okay, and I took a bunch of samples, are they all still going to have about the same mean? We're not, if my population, if this sample is a decent representation of the population, which is very likely is, how do I know it's likely a good representation of my population?
Randomly assigned treatments.
The randomly assigned treatments. Do you guys see what I'm saying here? Okay. All right. So knowing that, this is not the distribution that has to be normal. When we talk about this caused you guys a ton of problems on the test. Remember when I said, why did the number of successes and failures need to be greater than 10? And a lot of people said for the normal condition. Well, those samples weren't normal either, okay? It was the distribution of the possible p hats from the sample. And in this case, it's the distribution of the possible x bars from the sample. So our sample's our best guess at the shape of the population. As long as the sample isn't super crazy, doesn't have a ton of outliers, we're fine with how it looks.
So the only case where it would be like not normal is if there were a lot of outliers, like for the sample.
Yeah. Or like a super strong skew, which I don't necessarily see here.
If there was a slight skew, it would be fine.
Slight skew is probably fine because if the population is slightly skewed, the means are still going to be close to each other, which means, and remember what we're describing is all those means. We're not describing the sample itself. I have some visuals of that in a little bit if we still need it. Okay? All right. Independence. Here's a hint. You should not be using the words 10% for this independence check.
The like treatments are assigned independently.
Was it?
Is it like treatments are independent for each subject?
Individual responses.
The individual responses to the treatments are independent. Yeah.
So how do you know when it's saying?
It's how your normal, or I'm sorry, how your random, that 10% condition works when what we're doing is doing random sampling. That's not what we have here. So anytime you're checking with random assignment, that's when you would use that one. All right, now that we have the data in our calculator, can you guys go ahead and find the t and p value? You can go straight to the t-test and just do it from the raw data instead.
Scared me that it was a sneeze. I was like,
I thought it was someone like starting to throw up. I thought it was something like that.
To make sure your t-test looks like kind of what I have highlighted up here for you.
That's just so scary.
Are we good with getting these from the calculator?
Mine seemed very slightly off.
My guess is one of your numbers got put in differently. Everybody feel okay? All right, and then since 0.003 is less than 0.05, we can reject the null.